Okay, it is 3 minutes after the hour, and we are going to get started. So, again, welcome back, everyone. My name is Eric Culverson. I will be taking you through today's topics up to our demo at the end.
Idi?
So, let's talk about how we engage with each other. So, yesterday, we looked at how you're able to feed questions to me and how I'm able to respond. And one of the issues came up was, well, can we see the questions themselves? And unfortunately, that's not the case. The way the to webinar, go to meeting infrastructure works is that if I type a response, then everybody can see that based on how it's directed. Like I can either send that message back privately or I can send it to the group. But in this case, because we want this to be more dynamic and more real time, I'm not answering the questions by typing them in. Instead, I am
Open-aయిందా?
responding verbally. So, what I need to do and make sure that I do each and every time is to read the question step by step so that everybody knows what the question is that I'm actually responding to. So, I'll be the only person that can see the question, but I will make sure that I read it out before I respond. I did that yesterday, but perhaps not as carefully as I need to, and just recognizing that you can't see the question. So therefore, the way that I read it first, obviously establishes the
Idiana
anticipation for
imagine?
you as to what it is that I'm
Sir,
actually responding to. So with that, let's get started.
um,
In fact,
ఏ ఇంజన్
let's
డిఎస్పి
get
ఇంజన్
started.
అడిగానా?
If you have any questions, are there anything that we
Huh?
talked about yesterday that you'd like to
ఏ ఇంజన్
clarify or
డిఎస్పి ఇంజన్?
discuss before we move forward? We did an introduction yesterday to the overall
అదే అదే
platform
రైట్
versus
సైడ్
the
ఇమేజ్ మొత్తం ఏ ఇంజన్
device.
డిఎస్పి
We
ఇంజన్.
started talking about the AI engines, and we're going to end
Huh?
up with the AI engines
మీరు
today.
పెట్టుకోలేదేమో చూడండి.
But right now, we're looking at other aspects of the platform, in particular the processing subsystem. So that's where we are today. That's where we left off. That's what we're picking up this morning. So, any questions before we get started? All right. So, not seeing any. So we're talking about this overall processing subsystem, and as you can see from the slide, this encompasses the A72s, the R5s, and then this thing called the Platform Management Controller. And in the Versal ACAP, this is a really, really important block. In fact, if you look at this list, this is responsible from everything from booting up the entire platform to configuring the various portions. So that would be the adaptable engines, which means that we're writing to the programmable logic. So in a Versal ACAP device, you've got these different subsections, but the FPGA fabric is just like other FPGA fabric. We write to that with a binary file, and that always happens in frames. So if you look at the overall FPGA structure, there are frames that are used to write to each configuration memory cell in the FPGA fabric. So the platform management controller is responsible for setting that up. It also does security core functions. So things that have to do with perhaps tampering or someone trying to rig the device, as well as the secure boot. It's all managed within the platform management controller resources. If you're doing testing and debugging, this is also where the infrastructure exists to support that. It allows you to connect the JTAG cable or the high speed debug cable. Monitoring system activity. Once the system is up and going, this is where the interrupts are also fed back into, and it releases the processing subsystem from reset. So when we're booting up, we're starting up, this will be the controller for that. So it's a really important part of the overall um, device startup as well as the device operations. So when we talk about booting this, the PMC actually initializes the device via the boot pins. So the boot pins are tied high or low depending on what mode you're using and exactly what you're using to program the FPGA and the overall Versal ACAP. It then initializes the individual blocks, everything from AI engines to the adaptable engines to ultimately the processing subsystem. If the processing subsystem initialization is requested, then it's going to start up something called the PSM, which is the processor system manager. And then that completes the initialization for the processors themselves and also helps to manage the power domains. So you've got this restructure, the so-called PSM, which is actually a 32-bit version of the microblaze processor that's built with a triple module redundancy. So it's very reliable and it's programmed to perform operations that are specific to starting up and maintaining the processors. It also manages the local RAM for instruction data, the interrupt proxy, and then the register controls for the power islands. And the power islands are the full power domain for the A72s, the low power domain for the R5s. You also have I/O peripherals, and this is all part of the platform management controller. So the I/O peripherals basically are things like the advanced peripheral bus interconnect switches. So this is allowing the um, device to talk to external components as well as internal communication. So remember, this is all ARM based, so we're using the ARM protocol for interconnect. The I/O signals themselves are routed through, so that includes from the processing system to the low power domain, also through the multiplex I/O, and then through the extended multiplex I/O. And the difference between, of course, the multiplex I/O and the extended multiplex I/O is that the multiplex I/O are hard coded. So you have this not quite fully populated cross-point switch that allows you to determine which I/O are going to and which peripherals are going to be immediately visible during power up. And anytime we need more pins, then we route that through the fabric. So then that becomes the extended multiplexed I/O. Very, very similar concept to what Xilinx did with both the Zinc and the Zinc MPSoC family. Those I/O peripherals can, generally speaking, be divided up into two categories. You've got low speed peripherals, so you got SPI controllers, I2C, general purpose I/O, UART, CAN, FT, and then the high speed side, you've got the gigabit transceivers as well as the USB 2.0. So a lot of these peripherals have individual ways to do clock and power gating. That's a big part of the overall Versal ACAP, is being able to dynamically manage what's active and what's switching as a way of controlling power. Because if you think about this really broad chip, it's possible to really dissipate a lot of power. So there are lots of means and lots of things that you can do to mitigate that, and this is one of them. So the number of peripherals that are required directly is relatively small, and all these peripherals have the benefit of the ARM trust zone support. So that means that we can build in security features that will determine who can access certain peripherals and certain interfaces. So the way that multiplex I/O is organized, this is a set of pins that are a total of 78, and they are organized into three banks of 26 each. So if you look at the table, this is showing that multiplex I/O 1, 2, and this should obviously be a different number here. That was a typo on that part, but this is shareable across these two. So the overall bank itself is actually 52. So this is why this has the same label. But we can see the specific pins that are involved from 0 to 25, 26 to 55, and then finally up to a total of 78. So this is you selecting upfront which IO you want to use, which set of peripherals, and these are available immediately upon the device power up. Then you've got a fourth bank that is just going to be things that are dedicated to the platform management controller. So the boot mode selection, the JTAG interface to power on reset status error signals. This is a part of the overall configuration, but it's treated a little bit differently. These are all relatively low speed, maximum clock frequency here being 200 megahertz. And if for any reason we can't access this directly through the MIO, then we can use the extended MIO and route these through the programmable logic. And the programmable logic can also share these pins through relatively slow interfaces, basically about 100 megabits per second, but that's enough because all we're doing are things here that relate to configuration. Across the overall device, there is a ton of different interfaces and connections. The way we described this yesterday, we said that, you might not actually use all of these, but it's good to know they're there. As part of your system architecture, you're looking at these various blocks. And the main thing we want to do with the Versal ACAP device is take advantage of the integration. So that means having lots of communication, lots of interfaces between the different groups. So this slide talks about the interface between the processing subsystem and the PL. So from the adaptable engine, the programmable logic, so we've got ports that are going between these two, which also means that they're going between the power domains as well. So between the programmable logic and both the low power as well as the full power domain, because we're talking to the RPUs in the low power domain and the APUs in the full power domain. So this gives us a little bit more detail about this, and of course you can find this information in the data sheets and in the product specification guides as well. But the key takeaway from this is there's a lot of specific interfaces so that when you need to do interprocessor communication, or perhaps you got a kernel that's sitting in the programmable logic, or perhaps even a microblaze processor that's sitting in the programmable logic, that can very easily initiate as well as receive communication from either the APUs or the RPUs in the full and low power domains respectively. And that can either be cache coherent, or it can just be a basic AXI interface channel. Those AXI coherency communication paths take advantage of the Snoop control unit to maintain cache coherency from and between the individual processes, as well as maybe a processor that's running in the programmable logic. So you have two ways of doing it. You have the coherency extension, which is the ACE, and then you have the accelerated coherency port. The difference between them being whether or not it's one-way coherency or bidirectional. You also have connectivity from the processing subsystem and the PMC itself. So remember that the process management controller is actually part of this larger processing subsystem block. But because the processor, because the platform management controller is so important, it really is like its own little island. It has its own power rail. It does a lot of functionality, so it has its own communication channels to other parts. So here we've got communication from the processors to the PMC, or vice versa. We've got from the processing, from the platform management controller through the multiplex IO to the various clocks to the JTAG interface. So a lot of things get routed through the platform management controller, and hence the amount of connectivity that you see there. This also connects to the NOC interface. So the NOC is the network on chip, which during the initial device configuration, this is going to be handled with something called the MPI, which is the native programming interface. So when you see that term MPI, that's what that relates to. So this ultimately allows any master to potentially reach any slave. Remember that the NOC gets configured in Vivado. So you simply just pull down a piece of NOC IP in the IPI tool, and you select that this particular master is going to talk to this particular slave, and you give it information about the quality of service. So you're able to rank different pairs of receivers and transmitters in terms of their prioritization, because ultimately all of that is going to be mapped to the physical NOC. So you're going to wind up with some shared resources. So that sharing is managed by you specifying what the priority is for each of the set of receiver driver pairs that are being used there. So here's a little bit more detail about the processing system to the NOC interfaces. You can see there are quite a few, and it goes back to this same idea of across the device, we want to have as many different communication channels. So messaging, instruction, reporting, whatever your application calls for, you should find the appropriate connection between these subblocks. The interconnect itself and the processing subsystem, you actually have dedicated 128-bit wide AXI channel connections that go between the subsystems, and it kind of breaks down into two general groups. So you've got things that are lower latency, so there's less buffering there. So this would be like from maybe the APU to the NOC, or the RPU to the NOC, from the RPU to the on-chip memory, or to the tightly coupled memory. And we can see that it's, again, intended to be very, very low latency. Then you have other paths that are running at a faster clock rate. So you've got the APU to NOC, RPU to NOC, using the master ports, and then the main switch master port. And then you also have things like the APU to the cache coherent interconnect to the full power domain main. So a lot of this, not things that you are necessarily going to use, but as I said, it's better to have it than to not have it, because when you get down into the details of your design and you are architecting your system and you look at the different blocks and you want to establish effective, efficient communication channels, then you know you have these options. So the last couple of slides here talk primarily about the power domains themselves. So we've been alluding to this concept of having the different elements located in separate power domains. Now, why does that exist? So that you can effectively manage portions of the chip from a power standpoint. If necessary, if everything is running the low power domain, the full power domain, and you're using components within that, then so be it. You're getting the high level performance, you're getting the high level integration. But there may be times when you can scale that back, when you can save power by actually managing, individually being able to gate the power or turn it off, or put things into a kind of a sleep mode or a semi-sleep mode. So you've got two dedicated controllers that help with this power management. So the PMC is the main one. This facilitates the isolation of power domains outside of the processing subsystem. So this is like everything else other than just the processing subsystem itself. The processing subsystem is managed by the PSM. So this has the specific interface for the processors themselves, even though there may be other things within that overall domain. So when we look at the total chip, you've got the full power, low power, the PMC itself, the platform management controller, which, as we said, is kind of stands on its own. You've got the battery back domain, you've got system power, and then you've got a power domain for the programmable logic itself. And we can see which major blocks are included in each one of these. And all of these can be individually managed. The only one that can never, absolutely never be turned off is the platform management controller, because that's the one resource that is really managing everything. It's not just responsible for booting up and configuring the device, it's actually responsible for the ongoing maintenance, security, monitoring, everything, interrupt management. So this power domain is always active. In fact, if you put any of the other power domains into a sleep mode, then it would be the platform management controller that would be responsible for bringing them out of that mode. So this slide just takes the same information, kind of looks across the chip architecture at the APU cores, the RPU cores, and color codes as to which power domain all these are in. Now, we don't need to go into this in detail, but what you can do as a system architect is, again, think about your application, think about your system interfaces, the different modules, your power requirement, what's your power budget, and then look at perhaps using this and manipulating as a way to stay within those boundaries. So the ACAP device has a processing subsystem that includes the scalar engines, and that encompasses the APUs as well as the RPUs. Those devices use the same instruction set as previous families, so that makes it easier to migrate designs. The platform management controller is a centralized platform management controller for all designs. So everything that has to do with the Versal ACAP will be using the PMC. The I/O peripherals are used to connect external devices, use very industry standard protocols. You've got the multiplex I/O, which connect the I/O peripherals to the specific pins themselves. So that's just as it was in the previous family, it's a set of dedicated pins and you configure it. So that kind of thing takes place in a block called the SIPs, the control, interface, and processing blocks. So that's where you configure exactly which set of multiplex I/O you're using. And of course, there's going to be different possibilities there, but they're still not unlimited. And when you run out of the MIO, then you can take advantage of the extended MIO by going through the programmable logic. So you've got dedicated port interfaces, and those interfaces allow communication between these sub blocks, and they also go across the power domains because some of these blocks exist in different domains. Okay, question.